So I think we can start this session. And the first speaker is going to be Igor Broeckel from Bologna. So you have the 10 minutes.
All right, thank you. So let me first start by thanking the organizers for the opportunity to present my work today. So today I will speak about modular stabilization and the statistics of SUSY breaking in the landscape. And this work is based on a collaboration together with Michele Ciccoli, Anshuman Maharana, Kajal Singh, and Kuba Sina. So I will start by explaining the importance of Kähler modular stabilization in this context. Then I will briefly review different stabilization mechanisms that we studied, then I'll present our results, and then give a brief conclusion. Okay, so let me start by giving a short summary of the preliminary work done by Denef and Douglas in the beginning of the 2000s. And the important thing about the seminal work is that Denef and Douglas focus on the dilaton and the complex structure in the SUSY breaking scale analysis. So they neglected the contribution coming from the Kähler moduli, and I will explain why this can lead to problems. So Denef and Douglas basically started with a Kähler potential and a superpotential of this form. And by using these expressions, you can derive a supergravity scalar potential of this form. And as just mentioned, Denef and Douglas neglected the contribution coming from the Kähler moduli, so they neglected the F term coming from T. The reason for that is that Kähler moduli are stabilized only beyond tree level. So it was assumed that their stabilization would introduce only a small subleading corrections to the leading order picture coming from the dilaton and the complex structure. So by using this formula, Denef and Douglas assumed a distribution of the SUSY breaking vacua of this form. So we have a distribution of the F terms coming from the dilaton, the F terms of the complex structure, the depth of the ADS vacua, and a distribution function rho, which depends on F and lambda. And by assuming that the distribution of the SUSY breaking scale is basically decoupled from the distribution of the cosmological constant, we can assume the density function to be just a function of the F term. And in addition, by assuming the vanishing of the cosmological constant, we can rewrite the distribution of the SUSY breaking vacua in this form. And Denef and Douglas derived an expression for the density function of this form. So basically a constant distribution. But we will see that if we include also a stabilization of the Kähler moduli, this beta coefficient is not necessarily equal to 0. It will be equal to -2 in LBS and equal to 0 in KKLT. Okay, so why are Kähler moduli important? So we can rewrite the scalar potential in this form. And by using the no-scale relation, which you can see here, you see immediately that the third term cancels out, and we are left only with a contribution coming from the dilaton and from the complex structure, which you can rewrite in order to end up with this expression here. So you can immediately see that basically any vacua which has diw not equal to 0 leads to an unstable solution, since it gives rise to a runaway behavior for the volume mode. So a stable solution requires Fs and Fu to be equal to 0, or at least to be suppressed with respect to the F term coming from the Kähler modulus. And additionally, an important observation is that at tree level, the Garetino mass is in fact set by the F terms coming from the T mod from the Kähler moduli, since the no-scale relation implies a relation of this form. And another important observation is that soft terms are of order of the Garetino mass only for specific models, where the metal is located on the 7 branes, but not on the 3 branes. So for instance, Garetino masses for the 3 branes are set by the F term coming from the dilaton, which is non-zero due to subleading corrections beyond tree level only. So in order to determine Fs, we need to stabilize the Kähler moduli as well. So we see in order to study SUSY breaking statistics, we need to introduce Kähler moduli stabilization as well. And one way to do so is KKLT. KKLT is a stabilization mechanism that uses only non-perturbative corrections of this form to the superpotential, where the Kähler modulus is given by this expression, and little a, or more precisely this little fancy n, is a parameter that determines the nature of the non-perturbative effect. So by using this expression of the superpotential and the Kähler potential that we've seen before, we can write down the scalar potential, minimize it, and obtain these relations that are true at the minimum of the potential, and use these expressions in order to rewrite the Garetino mass at the minimum of the scalar potential, which gives us this expression. Now, There are several consistency requirements in KKLT, which can be summarized by the necessity of having an exponentially small W0. Okay, so we can see that in KKLT, the overall scale of the gravitational mass is basically determined by the value of W0, which is different in LBS, which is a stabilization mechanism that combines non-perturbative corrections to the superpotential and perturbative corrections coming from alpha prime corrections to the Kähler potential. Here we can play the same game. We can combine these two expressions to compute the scalar potential, minimize it, and obtain these two expressions, which we can use in order to write the gravitational mass at the minimum of the scalar potential, which is given by this expression. And here we can immediately see an exponential dependence on the string coupling GS. So the overall scale of the gravitational mass is determined primarily by the value of G string in LBS. Yet another behavior we can observe in the case where we use only perturbative corrections to the Kähler potential. So if we combine alpha prime and loop corrections to the Kähler potential, where the main leading contributions are displayed here, B and C are functions that are explicitly known only for very simple toroidal or antifolds, but are generally expected to be rather small values. So we can, again, play the same game. We can write down the scalar potential, minimize it, and then use the relation that we obtain to write down the gravitational mass at the minimum of the potential, which is given here. And again, since we, in order to have control over our effective field theory, we require a very large volume and a small G string, which translates in the requirement of having a very large value of the function C of U. So in this case, the gravitational mass is mainly driven by the value of C. So in all these three cases, we have seen that the gravitational mass is basically determined by W, G string, little n, and the function C. So in principle, if we know how these parameters scale in the landscape, we can basically write down the scaling behavior of the gravitational mass in the landscape. So it is a standard assumption that W0 squared is uniformly distributed as a complex variable in the complex plane, which we also assume here in this work as well. But there's a small caveat here, which I will mention later on. The distribution of the string coupling was checked by us to be uniform for rigid Calabi-Yau's, and was also shown to hold in more general cases by these groups here recently. So we will assume a uniform distribution of G string. The distribution of the parameter of the little n parameter, which determines the nature of the non-perturbative corrections, is still very poorly understood. But in general, we expect the number of states to decrease when we increase little n, since the 7-tadpole cancellation is more difficult to satisfy. So we assume this, let's say, phenomenological scaling of this parameter. And we take the same scaling for the function C, since C is a function of the complex structure and large values are considered to be more fine-tuned. So if we combine these four expressions and start, let's say, with LBS, we can simply compute the variation of the gravitational mass, which we computed earlier on at the minimum of the scalar potential, and replace all the variations of these underlying parameters with their respective scaling in the landscape, which allows us to extract the density function for the case of LBS. And as promised before, you can see here, it is not as in the result of Danoff and Douglas, not a constant function, but in fact depends on the gravitational mass with a beta coefficient -2. So if we use this density function and perform integration, we end up with a logarithmic distribution of the gravitational mass in the landscape. And since in LBS, the relation between the gravitational mass and the soft masses is given by this expression, we can conclude that LBS vector feature a logarithmic distribution of soft terms. We observe a different behavior in the case of KKLT, where if we play the same game again, we perform the variation of the gravitational mass in KKLT, replace the parameters, and extract the density function. We see that in KKLT, we indeed observe a more or less constant distribution function, which results in a power law distribution of the gravitational mass in the landscape. And again, since we have a very similar relation between the gravitational mass and the soft masses as in LBS, we can conclude that for KT vector, we observe a power law distribution for soft terms. So in LBS, we have a logarithmic distribution, and in KKT, a power law distribution. However, there is a small caveat here. This result rely heavily on the assumption of a uniform distribution of the tree-level superpotential. However, very recent constructions done by the McAllister group in the States have shown that if you construct a model which realizes this important constraint of an exponentially small W0, you can obtain a relation between W0 and the string coupling, which is given here. So tau is basically 1 over G string. So you get a functional dependence of W on the G string. So all these prefactors are not very important. The important insight here is that there is a dependence between W0 and G string. And if you use this, so if you use this result, you can obtain logarithmic scaling in KKLT as well. Now it is, however, not yet known how general these constructions are. So it is important to understand whether these recent constructions are representative of the landscape or whether they are, let's say, an outlier. So whether a statistical approach with these vacua are justified. But in principle, one could realize logarithmic scaling in KKLT as well, which was shown by this group. Okay, so in the case of purely perturbative stabilization, we can again play the same game again. We can compute the variation of the gravitino mass and then replace the variation of the parameters with the respective scaling in the landscape and extract the density function for the purely perturbative case, which is very similar to the KKLT result. So in this case, however, we have a dependence on this parameter k, which determines the specific scaling of the function c. So we get a qualitatively similar result to KKLT, for instance, if we set k equal to 7. So overall, we obtain also power law distribution for soft terms in this case. Okay, so let me come to my conclusion. We have stressed that Kähler modular stabilization is a critical requirement for a proper treatment of the statistics of SUSY breaking. So different no-scale breaking effects that we use to fix Kähler moduli lead to different dependencies in the gravitino mass on the flux-dependent macroscopic parameters such as W0 and G string, and so on. In LDS models, we have seen a logarithmic scaling of the gravitino mass in soft terms. And in KKLT and in perturbative stabilization, we observe a power law distribution. However, this might be not general, so we might get a logarithmic distribution in KKLT as well. So determining which distribution is more representative in general for the structure of a flux landscape basically translates into the question of which vacua are more frequent, LBS or KKLT. So, and one might say that since LBS vacua need less fine-tuning and they exhibit a larger parameter space, one might think that LBS models are slightly more favored, but a definite answer would require more detailed studies. Okay, that's all I wanted to say. Thank you.
Thank you, Igor. We have time for one quick question.
Okay, sorry.
Can I ask a question?
Yeah, sure.
Sure.
Yeah, so just, okay, basic question. So you said that in LVS, the gravitino mass is proportional to exponential of 1 over GS.
Correct.
But you also want the GS to be very small. So I wanted to ask if there is a tension between having GS very small to control your expansion and having the gravitino mass sufficiently big. For very small GS, also the gravitino mass will be very small. So I'm just asking if there is a phenomenological tension in requiring these two things.
Well, we get reasonable values for expected values of G string. So we get gravitino masses of around 10 to 10 GeV, I think, for values of around 1.1, 0.1.
I see. Okay, so it's quite big.
Yeah, it's still quite big. Yeah.
Okay, thanks. Another thing, super quick. You said that the distribution for GS in the landscape for rigid Calabi-Yau is constant.
Yes.
But then I think I either missed or you didn't say what is the case for non-rigid Calabi-Yaus?
Oh, well, for generic non-rigid Calabi-Yaus, it's not quite known yet. There was a study by what was it? A recent study by Blanco, Pelado, Sousa, Auricular, and Wachter, which I don't quite remember which specific example it was, but it was not a rigid Calabi-Yau. I would need to check.
Because
which explicit example it was, but they checked for a non-rigid Calabi-Yau as well, and it was uniform as well. Yes.
Because the hypothesis of rigid Calabi-Yau seems very strong for me in order to make a generic statement about the landscape. If you pick a generic
definitely.
rigid.
So all these results rely heavily on these assumptions, on the specific distributions of these parameters. So one natural extension of this work would be to check the distribution of G-string for more general geometries by deploying them.
Exactly, yes.
The databases.
Okay, so yeah, sorry to barge in. Let's thank Igor again and make way for the next speaker.